I just do what they tell me to do. Okay. Newton's three laws.
Does this chapter relate to the last three chapters that we did?
They're all mechanics, yeah. Yes, a little bit. Not so direct, but yes. Okay. Got this? Yes. Come on. Right. So Newton. So like I said, if you want to be important in physics, you need to have at least three laws. Otherwise, nobody cares about you. So Newton's three laws. So we've already seen Newton's second law. So what's Newton's first law? I'm sure you remember it. If you don't remember from high school, if a body is at rest, it remains at rest. Or if it's in motion, it will move with uniform velocity until acted on by a force. So in other words, if something's not moving, it will continue not to move unless a force acts on it. If something is moving at a constant velocity, it will do so unless a force acts on it. Yeah? Or no? Which part? No, it's not okay. I don't believe you. You can ask questions.
You said if something moves,
yes.
Continue move.
Yes.
But like the ball is moved and nothing stops it.
But it stops. Yeah. So what's happening there? The ball is moving, let's say 10 meters per second, and if it was in space, it would continue to move. But in real life, what's happening is that there's air. Yeah, and the air is a force that's pushing it. So if this, if this was in, do you know this? Deep space? Deep space. So like, hang on. Sun, Earth, you live here, okay? And deep space would be away from everything. No gravity, nothing. So over in deep space, which is over here on my picture, if something is moving, it will just move like this forever. We do not live in deep space, so we never really see this in real life, which is what you're saying.
What if it was in a vacuum?
In a vacuum, yeah, but I mean, at least in my life, I don't usually visit vacuums.
But like, is it possible? Is that the whole?
Yeah, no. If it was in a vacuum, yeah, it would be the same. But you see, the problem is a vacuum has to be in something contained, so it will continue to move until it hits the wall. So.
But then, what about gravity? Like, gravity still acts in a vacuum.
Oh, that's true actually. So it would still fall down and hit the wall. So why would you need to be in a vacuum on the International Space Station? That's the closest. Okay, so please write this down because this is such a common question in the exam. They love asking about Newton. So you don't have to have it word for word like this, but it needs to have this idea that it's at rest or constant velocity until a force acts on it. Yes?
We can create a magnetic and an electric field.
Yep.
Can we create a gravitational field?
You're doing it right now, creating one. Yeah, everything creates one. What you really mean is, can you make it bigger, stronger? Yeah. No, unfortunately not. Because it doesn't behave the same way as the other two. Do you know?
Not even if we accelerate the object and super speed and nothing?
Nothing. Is the gravity...
Only if we increase the size?
Or the mass.
The mass.
Yeah. Gravity is only a function of the mass.
Yeah.
Without changing the mass, nothing happens. Whereas at least with the electric and magnetic field, you could get a stronger magnet or a higher voltage. to make a stronger field, but with gravity, unfortunately not. Because if you could have cool things like hover cars and stuff like this, but no, didn't work out. Okay, you got Newton's first law? Yeah. So here is a Fuang. This is the closest example to Newton's first law in real life, but it's not perfect. An object will stay at rest unless a force acts on it, like here at the foot. And then it will move with constant motion unless a force acts on it, like the net. Yeah, but of course in real life it'll also be the air as well. So it's not perfect, but it's a good example of Newton's first law, both the rest and the constant speed. So you don't need to write this down. It's just a picture to help you understand. Okay, next one. Newton's second law. Now you should remember that. We did it like a week ago. What's Newton's second law? What? I don't get your reference, I'm sorry. What's Newton's second law? Yeah, so force is the product of mass and acceleration. In the exam it's a little better if you can write a sentence, even though it's exactly the same as F equals M, right? Yeah. Product is another word for multiply. Did you hear that wrong? What did I just say?
Product is another word of
for what? I know you missed the most important part. Product is another word for multiply.
Yeah,
Multiply. Okay. Do you have that? Yeah. So, here's a picture again to help you understand this one. So, it's F equals ma is a formula which we did last week. So, if you increase the mass, of course you need more force. Or likewise, if the velocity increases a lot, it means that's a lot of acceleration, which also means a lot of force. Okay, Newton's third law. One left, and again, you probably know this one from high school if you studied it before. So, for every action, there is an equal and opposite reaction. Oh, Fuang, do you know how many students I had in physics this morning? 2.
Yeah.
No.
Anna.
Yes. No. Those are the 2 who worked there.
So only have Nisa and
Yes. The class was very quiet. Very quiet class. Okay, do you have this written down? For every action, there is an equal and opposite reaction. Okay. So, here's an example of this one. This is the action. The air comes out the back of the balloon. And this here is the reaction. The balloon moves forward. Now, Newton's third law can be a little bit difficult, and part of the reason it's difficult is because often the teacher doesn't explain it well and the examples aren't clear. So, when I say every action there's a reaction, really I should maybe say for every, like the simple English for it is, you do something, something happens. Okay, that's really the simple way to put it. So you do something, something happens. Now you can't say that in the exam. But, you know, for example, here's my action. I rub my hands together. So what's the reaction? My hands get warm. And sound as well. Yeah. The other example is I push against the wall. The wall pushes against me. Yeah. The air comes out the back. The balloon moves forward. You know. So it's not always clear what the reaction is. That's my point. But there is a reaction. There's always a reaction. But it's not always clear maybe what that reaction is. Okay? Right, so this is wall pushes U. So the example here is we have a force here. What force is this? Gravity or weight, yeah. Weight. So there's a weight here. So this will move, but it stops here. The weight is not gone. There's still a weight force here. Why did it stop? The table is pushing back up. So here, this equals this because it's not moving. The reaction force, that's the green one here, this up force, is the force provided by the reacting object. So in other words, it's the force from the thing that's pushing. I think it's worth writing this down. Reaction force is the force provided by the reacting object or reacting obstacle.
So for Newton's laws, do we have to memorize them? Like first law is the specific one?
Yep.
Do we mix them up?
No, you lose marks in the exam if you do that. So remember the order as well. Newton's first, second and third law. First one is the at-rest one, the second one is the formula, and the third one is the action-reaction one.
Is there a reason for that? Like first and third?
Order of
That's why you need
discovery?
I don't know actually. Maybe it's just the order he numbered them. I don't necessarily think there's any reason that they have to be in that order. But the first, well, it might be an order of discovery. The first of Newton's laws was originally discovered by the ancient Greeks. So that would be the oldest of the three. So yeah, there might be a discovery order to them. But the first law is the most basic. It's the one that's been known for the longest, I think. Okay. Here's a simple question for you to try now. It won't cause you too much trouble. A 20 kilogram mass is on a table. What's the reaction force? Can you calculate that, please?
196.2.
What did you get?
196.2.
Sounds about right. Yep. So what's happening here?
Is negative 196.2.
Depends on the direction.
It does indeed, yes. And you don't really have a choice about the direction. This is mg, this is or. It's balanced, it's equal, so or equals mg, which equals, what did I say it was? 20 times 9.81, which equals 196.2 newtons up. Yeah. Okay, continue. Continue? Yeah, okay. Okay, a block of mass 200 kilograms is on top of a table. For some reason, a man tries to lift the block up by using a rope, and he pulls with a force of 1,000 newtons, but the block doesn't move. What's the reaction force? Okay, I'll draw it, and I'll let you calculate it.
Just a good question.
Yeah.
What was the units for?
Oh, newtons. Yeah. Um,
5. What was it?
This question I'm going to draw it. So what's happening here is there's a 200 kilogram block. There's a rope here. There's a man here. That's him. And he's pulling up on the rope with 1,000 newtons. Now, in fact, that's not strong enough to lift the block. The block doesn't move. We still have our weight, and we still have our reaction force from the table. So I'll give you a minute. I want you to try and work out what is that reaction force. The reaction force is what?
803.8.
I don't believe so. What is it?
I was thinking like it's because the acceleration that's going up.
962.
Nope.
962.
962, yes.
Yeah, what did I say?
You said 100.
Oh, sorry, I meant 900.
That's okay. Right. So what's happening here is it's not moving. If it's not moving, it means that the ore plus 1,000, this is from the table,
Question.
and this is from and this is from the man. That has to equal the weight. Yes.
Isn't the R downwards?
No, it's upwards. The table is still pushing up. The table isn't pulling the block down, it's pushing it up. Or equals W minus 1,000. Or equals mg minus 1,000. Or equals 200, 9.81 minus 1,000, which equals 962 newtons.
Yes, but the man is pulling up
Yes,
by 1,000.
correct,
But it's not moving because
correct.
Because
the total force going down is 1,962.
Correct,
The man is pulling up 1,000.
correct.
So isn't the rest downwards 900 and...
No, you need to make both sides equal. You need to make both sides equal.
Yes, it's
so
It's a long day.
it is a long day. It's even longer for me.
how
Yeah.
I thought of it is like the acceleration is 9.8 going downwards, so I calculated the acceleration going upwards and that was 5.
No, there is no acceleration here. It's not moving. There's only force.
Yeah, but then if the acceleration is like if it's lower than 9.8, so it's obviously be going down more. It's not greater than the one going.
I think this line of thinking is dangerous.
Yeah.
I think you should only be thinking about forces at the moment. The force up must equal the force down. Simple as that. So R plus 1,000 equals W.
So R is the force applied by the table.
Correct.
Okay.
So the R is from the table, the 1,000 is from the man, and the W is from the earth pulling down. Okay. Is that okay now? Yeah? We'll do another one, I think. Okay, I want you to try this by yourself, and then I'll do it. It's very, very similar. The only difference now is there's an angle, 45. That doesn't change it too much, because it just means you have to resolve it into X and Y. Yeah. Give it a try, and then I'll do it.
Did you draw it?
Yeah, I'll draw it. It's 200. He's dragging it with a rope. The rope makes an angle 45. He pulls with 1,000. What is the reaction force? The table is... Okay, so what's happening here? It's the same man, except this time the man has given up trying to lift it and has decided to pull it. So it's still 200, but he's given up and now he's pulling it. And it's 1,000 newtons, and the angle here is 45. there's still going to be the weight and the reaction force from the table. So my question here is, what is this reaction force? I want to know this. Okay, try that. Sounds plausible. It should be more than the last answer, but less than 1962.
Yes.
Did you draw and write?
No.
Please do.
Are we going to do friction today?
Let me think. No, I think we'll split this lesson up into two halves. We'll continue it next time. So I think we might get to the friction next time then. No, it should be more than the last answer. Yeah.
125, 1.9.
0.9. Yeah. You don't need the 0.9. 125.
1252.
2. Yeah.
1255.
Oh, yeah, 1255.
1255.
Long day. Breakfast. Lunch. So that's okay. Okay. Are we finished? Can I do this one? Omar, you look confused. Did you get an answer? We'll have a look at this one now. Yep. So we have here, the key here, Omar, is we have to resolve this into x and y. So this is 1000 cos 45, and this one here is 1000 sine 45. If you look in the vertically, it's not moving vertically. It's only moving horizontally. So vertically, or plus 1000 sine 45, that should equal W. Because it's not moving this way, so this one should equal this one. It's balanced. So that means or equals W minus 1000 sine 45 equals mg minus 1000 sine 45. That's equal to 200 9.81 minus 1000 1 over root 2. 200 times 9.81 minus 1000 over root 2. What did you get?
1255.
1255.
I don't know. It's like my calculator is being weird today, which I know doesn't make sense because it has to be me that's being weird. 1255. Okay. 1255 newtons is the reaction force here. Yeah. Yes.
When do we choose the equivalent of the sine angle?
You might have missed that secret I gave in class. Does anyone remember my secret trick for which is the cos and which is the
I
sine?
know which is the cos of the sine, but no, like which one to choose.
Oh, here?
Yeah.
Vertical. Because you only care about this. You don't care about this way. So you have to look at the one that's going up and down. Yeah, because you only care about the reaction. Yeah. Yeah.
Yeah, I just gave the vertical component. I thought that was the answer, but it's a different force, is it?
Yeah, this is the force from the rope, and this is the force from the table. So this one is from the rope, and this one is from the table, and this one is the weight from the earth. And these two added together must equal this one. Does that make sense?
But isn't the force from the rope horizontal?
It has a horizontal and a vertical component because it's at an angle.
So what happens if we calculated 1000 cos 45? Like
That's the horizontal force. That's how much force is being applied horizontally. You could use F equals ma to get the acceleration horizontally, because it is going to accelerate along the ground as he pulls it. Do you know? but it's not going to accelerate vertically because its height doesn't change. It stays the same height, but it does move across the table. So it will have an acceleration this way, but no acceleration this way, because the forces up and down cancel. There's only a horizontal force. It's like the opposite of projectiles. In projectiles, as it moves, there's only the down acceleration and none horizontally. It's literally the opposite of that. There's only the horizontal acceleration, but nothing's happening vertically. So that's what the 100 cos would be, a horizontal acceleration, accelerating force.
So, like, we have to calculate the vertical component plus the R to show that, to show why the object is not going upwards.
Well, you have to say, yeah. That's it. If R plus the, 1000 sine 45, if that was bigger than the weight, what would happen?
It would fly.
It would fly up, yeah. In other words, you'd pull on it and it would jump up in the air. If it was equal W, it's what we have. It stays on the table. But what happens if it was less than W?
The table would break.
The table has broken and has fallen through the table.
If it was, but it is less than W.
No, it's not. It's equal to W. It's balanced.
But then, okay.
The only way this could be smaller than this, that means that this is bigger than this, is if the weight has 1, the table has broken and it's fallen down now. But at the present, they're balanced, they're equal.
Oh yeah, they're both equal. Okay.
They're both added together are equal, yeah. Okay, when's our next physics class? Is it tomorrow or Friday?
Friday.
The Friday double class? 2 hours?
One time.
Single hour?
Yes.
You sure? Oh, it doesn't matter. We'll finish Newton's 3 laws on Friday. So you don't have homework from physics. So you could use this as a chance to just...
your homework from that.
Well, I was going to just say, look over your physics notes and just make sure there's nothing that you still don't understand that you need to ask questions on. So you could use this evening as a chance to read your notes and make sure you're good for everything. Because if you felt something was still confusing you, we can give some time to it in class.
So we only give, we only have tutorials for math, right?
Again?
Yeah, because with the physics, I do the homework in the class at the start, so this is the reason why I don't do a tutorial. Whereas with the maths, I don't. I leave everything for one class. Because
they have the answers.
Well, the answer at the back, but also it's a bit different because the physics, each question is a different problem, and you kind of need to see how it was done. Whereas the maths, it's more like quadratic, another quadratic, another quadratic. You know, you don't need to see everything done.